Selicato from CNR IRSA. I'm sorry for not being in person. Virginia and I really wanted to join you. This presentation is part of ongoing work within the PRIMA project NexusLabs, where we are developing and testing tools and approaches to operationalize the WEFE Nexus in real studies. I'm presenting on behalf of our team, Virginia Rosa Coletta, Alessandro Pagano, and Raffaele Giordano, mainly from CNR IRSA. Today, I will show how participatory system dynamic modeling, PSDM, can support the operationalization of WEFE Nexus. This slide summarizes what is often missing when we try to scale WEFE solutions. First of all, there is an integration gap. We have many good sectoral tools, but they produce fragmented outputs, and the trade-offs across WEFE often remain implicit. There is another gap, the engagement gap. Even strong evidence does not automatically translate into action because stakeholders may not share the same system picture. And finally, there is a scaling gap. Enabling conditions are rarely tested, so barriers such as capacity, trust, and enforcement tend to appear late when implementation is already difficult. Our argument is that PSDM helps address these gaps by turning evidence into shared scenarios that support co-learning and makes trade-offs and barriers visible before implementation. But what is a PSDM? The starting point is that WEFE challenges are driven by interactions and feedback loops. For example, between water availability, agricultural demand, pollution pressures, and ecosystem condition, often with delays and nonlinear effects. PSDM makes these relationships explicit and lets us explore them through scenarios. On the input side, PSDM brings together three types of evidence. Results of sectoral models related to hydrology, agriculture, ecosystem, and energy. Monitoring data, for example, from sensors, observations, and KPIs, and stakeholder knowledge, constraints, priorities, perceptions, and what is realistically feasible. On the output side, PSDM produces integrated WEFE indicators, makes trade-offs and synergies visible, highlights policy options, and this is very important for scaling, helps identify barriers and enabling factors that may block implementation. So PSDM is an integration and decision support interface, not a replacement for sectoral models. This slide explains why we describe PSDM as a metamodel. A metamodel is basically a model of models, an integration layers that connects sectoral models, monitoring data, and stakeholder knowledge through a shared set of bridge variables between sectoral models. For example, water availability and water quality, irrigation demand, agricultural productivity, and ecosystem condition. These are the variables that let different sectors talk to each other. PSDM also orchestrates sectoral models without replacing them. Of course, an hydrological model remains the best tool to represent distributed hydrological processes, and the monitoring remains best for point observation. PSDM uses the results as input, but it works at an aggregated sub-area scale to explore system-wide implication. Third, PSDM produces integrated indicators and implementation insights, meaning not only what improves, but also what may prevent implementation. And this is where enabling variables come in. Alongside the hard dynamics, let's say physically based ones, we introduce readiness factors such as for example, farmers' training and awareness, institutional capacity, public trust, and enforcement. These factors shape if solutions actually work at scale. Here we summarize what PSDM can deliver in a form that is useful for a policy brief. We start from three sources: monitoring evidence, sectoral model outputs, and stakeholder knowledge. I would like to highlight that the key point is that aggregation and harmonization turn fragmented evidence into comparable decision-ready scenario inputs. So we can work at a shared sub-area or basin scale rather than at the level of individual measurements. The second step is the scenario comparison dashboard. Here, PSDM helps compare a baseline and alternative options and not only see what changes, but also why it changes. Finally, PSDM supports packages of measures and sequences. So what to do first and what later, because implementation depends on enabling conditions. So now again, PSDM turns evidence into shared scenarios that support co-learning and implementation planning. Once the model is ready, we can turn into a simple dashboard that stakeholders can use. On the left, you see the control panel. Each policy option works like a slider. So 0 means not implemented, 1 means fully implemented, and between 0 and 1 we mean partially implemented. So we can start from business as usual scenario and then test different combinations such as improving irrigation scheduling, fertilizer management, biodiversity actions, and so on. The point is not to find the perfect numbers or the perfect combination, but to explore realistic options together and understand what changes what. On the right, we add the question, how hard is it to implement this scenario? The gauge shows an overall sustainability cost. Of course, not in euros, but is a combined score that reflects implementation difficulty. We consider three types of cost. Economic one, so money and resources needed for technology, training, and monitoring. The social cost, the effort, and the acceptance, for example, behavior change, equity concerns, and the institutional cost, the capacity and the coordination, for example, rules, enforcement, and workload. Here, PSDM is used as a co-learner where stakeholders compare scenarios both on results and on how feasible they are to implement and analyze cost-benefit evaluation. A key point for scaling up is that the same measure can work very differently depending on readiness. For example, because of delays, low adoption, and weak compliance. On the left, you see the mean readiness dimensions we should test in WEFE scenarios that are institutional capacity, data and monitoring availability, public trust, and stakeholders buy-in and enforcement and compliance. On the right, the idea is simple. Stakeholders can adjust policy levers that are the sliders, but outcomes also depend on these readiness constraints. This is how we can identify barriers earlier and discuss what enabling actions are needed before implementation. Now we move on the proof of concept in Greater Chania grid, where we show how different inputs feed the PSDM. As I told you before, PSDM combines three input sources to build three input sources. First, monitoring data, like a soil organic carbon, porosity, infiltration, and water retention. In the model, this helps us parameterize soil water processes and check if scenarios assumptions are realistic. Second, input from sectoral models. Here, for hydrology and allocation, such as a WEEP, providing groundwater recharge and withdrawal, inflows, and water availability for irrigation. These define boundary conditions and help fill gaps when monitoring is incomplete. Third, stakeholder knowledge, for example, let's say practical principle for smart irrigation and information on adoption constraints, priorities, and trade-offs. This is used to set adoption and readiness levels and co-design realistic scenarios. Again, an important aspect to underline is that PSDM does not use data as a single sensor. It aggregates information into sub-areas because it meant for larger scale learning and planning. Here is one concrete example of how monitoring data becomes a PSDM input. On the left, we have field evidence on infiltration capacity measured in different locations by TUC, under the tree and in the middle of the field. We translate these measurements into a simple infiltration capacity index, IC, scaled between 0 and 1, and aggregated at sub-area level. Then we connect this input to the model with a very simple link in the equation in the middle. If infiltration capacity is higher, the soil retains and absorbs water better, so irrigation water demand decreases. Finally, PSDM propagates this effect across the system. So lower irrigation demand improves the irrigation balance, reduces the water stress and the water cost. And this influences agricultural profitability and overall agricultural sustainability. Thus, a local monitoring dataset is not used point by point, but is covered into an aggregated input that helps stakeholders understand how soil conditions can affect basin scale outcomes. This slide shows where that monitoring input enters in the PSDM and what comes out. On the left, you see a simplified view of the agricultural module. In blue, we highlight the part of the model related to irrigation demand and water balance. This is where an input like infiltration capacity can reduce irrigation needs. From there, the effect propagates the chain, obtaining an aggregate indicator that is agricultural sustainability on the right. The plot on the right is a simulation output over time of the agricultural sustainability, and it is shown by sub-areas. The key point is that these curves are not point predictions for a specific farm or sensor location. They show general trends at basin, sub-basin scale to support decision and scenario comparison. This is a second example, this time using sectoral model outputs instead of monitoring. On the left are typically WEEP monthly outputs, groundwater recharge, spring or river inflows, and allocation flows. WEEP gives us a solid hydrology and water allocation baseline at basin scale. In PSDM, we import these values as an input for each groundwater body, and we can also apply a simple scenario stress factor, for example, a climate change reduction over time, as in the equation. PSDM takes the WEEP recharge and adjusts it under a scenario, then uses it as a groundwater supply. Then the effect propagates to the model. So we move from groundwater supply to groundwater availability, groundwater use, and this affects irrigation and drinking water balance, the level of water stress, and finally indicators like agricultural sustainability. So WEEP provides the hard hydrology numbers, and PSTM turns them into shared scenario that stakeholders can compare and discuss. This diagram shows where WEEP inputs enter the PSDM water module. Recharge influences groundwater supply and availability, which then interacts with the water demand and allocation. The point is not to reproduce a distributed hydrological model, but to represent the main feedbacks and balances that matter for scenario learning at sub-area scale. Here we show how variables from the water submodel connect to agriculture submodel. It reinforces that PSDM is useful to understand cross-sector chains, how a change in our place can affect outcomes in other sectors. And again, what we look at are relative threshold of a trend of agricultural sustainability over time at sub-area level. Now, the third input source that is the stakeholder knowledge. We use information from workshops and or surveys, for example, skills gaps, training needs, and willingness to adopt improved practice. And we translate it into a simple training and awareness index between 0 and 1 for each sub-area. This index then becomes an input to the model. In this example, low training means low adoption of good practice, so fertilizer pressure stay high. That increases nutrient loss and water quality declines for both surface water and groundwater. The small plots at the bottom are the overall trends over time of model outputs aggregated by sub-area. Now, PSTM allows us to run also scenarios. In this application, we simulated 4 scenarios from climate stress to agroecological practice. On the right, I show the model outputs here for scenario 4 related to the adoption of agroecological management to improve soil, water quality, and long-term sustainability. For key indicators that are water balances, groundwater quality, and surface water quality, soil degradation, soil erosion, and agricultural sustainability. Here I show what stakeholders actually interact with once the PSTM model has been built, a simple interface. We focus on scenario 4, so the agroecological practice, but the logic, of course, is the same for any scenario. Each slider represents a measure and the value goes from 0 to 1. 0 means not implemented and 1 means fully implemented. In between, we represent partial implementation or gradual rollout. At the center, the gauge summarizes the overall sustainability cost. Again, this is not money, but it's a composite indicator that captures how difficult implementation may be when we consider economic, social, and institutional barriers together. So this interface becomes a shared space for discussion. Stakeholders can test options together and see how outcomes and feasibility move. From this kind of interaction, 4 co-learning messages usually emerge that are packages matter, trade-offs become visible, feasibility is shared, and a common agreement emerges. To conclude, PSTM acts as an integration interface. It connects sectoral models, monitoring evidence and stakeholder knowledge into shared comparable scenarios. It's also important to be clear about what PSDM is not. It's not a detailed hydrological or sectoral model, and it's not a point scale monitoring tool compared to a distributed or semi-distributed hydrological model. PSDM is much more aggregated. It works at sub-area level, as I said before, and compared to sensor, it does not describe what happened at a single point. It simplifies and aggregate information. So why is this simplification justified? Because the PSDM adds is not more spatial detail, but more integration and usability. It links water, energy, food, and ecosystem, makes feedbacks and delay explicit, and includes readiness factors like data availability, capacity, trust, and compliance that often decide whether a measure we will work in practice. In other words, PSTM helps move from data to dialogue. It translates aggregate input into simple dashboard that stakeholders can use to learn together and negotiate trade-offs. And finally, PSDM supports actionable pathway, not just single measures, but a package of end sequencing co-designed with the stakeholders. Thank you for your attention.